friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts related to the probability theory and statistical inference. So, if you recall that in the last two lectures we had talked about two properties of the estimator. They are unbiasedness of an estimator and efficiency of the estimator. Now, in this lecture we are going to talk about two more properties. One is the consistency and another is the sufficiency, right. So, what is the meaning of consistency and sufficiency? For example, if you say what do you really mean by consistent? I mean, consistent means if you try to repeat something, then the same thing is happening again and again, and the number of times the things are not happening, that is very less, right. So, you can say that the person is consistent. For example, if you take a help from one of your friend, and every time the friend is helping, you will say that okay, the friend is dependable and the friend is consistent in helping the people. And similarly, if suppose you have couple of friends and there is one more friend who is very dependable, and sometimes you make a statement that okay, means having a friend like you is more than sufficient in my life. What does this mean? That means you can always depend on him, and whenever in your life whatever the needs you will have which are to be fulfilled by a friend, you do not need many friends, but only one friend is sufficient. So, the similar story is with the estimation also, that whenever we are trying to estimate an unknown parameter by a statistics, which is a function of random variables that will be dependent on sample. So, every time you generate a sample, the values are going to be changed. So, now what is really happening with the estimator when the sample size becomes larger? That is the property which is related to the consistency, and sufficiency is the property of the estimator which is trying to explain that how much the estimator is capable of explaining the information which is contained inside the statistic. So, let us try to understand now this concept in more detail, but before that, do you recall or do you remember the definition of convergence in probability? I am sure yes, and if you do not remember it, I will say pause the video, first revise the concept of convergence in probability, because we are going to use here, and consistency is simply the convergence in probability. So, okay, so with this aim we try to begin our lecture now. Okay. So, now you see, first we try to understand what is the property of consistency of an estimator. So, we expect that in case an estimator is good, then as the sample size increases, the values of the estimator should get closer to the parameter being estimated. That means, if you try to estimate say for example, the population mean mu by say sample mean say x bar, which is dependent on the sample size n. So, as n is increasing, then this value will become more dependable in the sense the difference between say this x bar n and mu will become say smaller. Right. Now, if you try to recall, have you done this type of property in the past? Right. Think about it. This property, that as the sample size is increasing and the values of the estimator are getting closer to the parameter being estimated, is referred to as consistency, and this is a large sample property. It means you cannot establish or you cannot talk about the consistency in case if your sample size is small, and the meaning of the consistency of an estimator is valid only when the sample size is large. So, do you remember the definition of convergence in probability? This was like xn convergence in probability to x, that is xn is tending toward x as n goes to infinity, if probability that absolute value of xn minus x is greater than epsilon is going to 0 as n goes to infinity for all epsilon greater than 0, or the probability of absolute difference of xn and x is smaller than epsilon goes to 1 as n goes to infinity for all epsilon greater than 0. Right? I had explained you the meaning of this expression earlier. Now, you try to see. Now, we try to define that how can you define the consistency of an estimator, right. So, let this theta 1 hat, theta 2 hat, theta n hat be a sequence of estimator for the parameter theta, right, where this theta hat n means theta hat is a function of x1, x2, xn, where this sample size is indicated here as n in the subscript. So, that is indicating that theta hat is a function of n, right. So, now we say that the sequence theta hat n is a consistent sequence of estimator for theta if for every epsilon greater than 0 probability that the absolute difference in the values of theta hat n and theta is greater than epsilon is tending to 0 as n goes to infinity, and this is valid for all values of epsilon greater than 0. Or equivalently, you can say that the probability that the absolute difference between theta hat n and theta is smaller than epsilon is tending to 1 as n goes to infinity. And you see that is expected. You are trying to estimate an unknown parameter, theta here is unknown, and you are trying to say that you are trying to estimate it by here estimator theta hat n. So, now what are you trying to say? This estimator is going to be good if the difference between theta hat n minus theta is as small as possible, right. So, you are trying to say that in case if I try to take the deviations which can occur in the positive and negative direction both. So, we try to consider here the absolute value, and the probability that the difference between theta hat n and theta is less than epsilon. The probability of such an event is tending to 1 as n goes to infinity, where this epsilon is greater than 0, right. So, what are you trying to say? That as we are trying to increase the sample size, that means in case if I take an example of sample mean x bar n to estimate mu. So, as you are trying to take the sample size from say 5 to 10 to 100, 200, 5000 etc., this value of x bar n is increasing, then the value of x bar n is getting close to mu, right. This is what we mean. Okay. Now, if you try to compare this definition of consistency with this definition of probability, that is the convergence in probability, then what do you see? That they are the same thing actually, right. And this definition is simply saying that as the sample size increases, the probability that theta hat n is getting closer to theta is approaching 1, right. So, this means that theta hat n is getting closer to the parameter theta as the sample size n grows larger, and we can indicate the same thing by saying that theta hat n is converging to theta in probability. If you try to compare this statement and here this statement, you simply have to replace here x n by theta hat n and x by here theta, and you get here the convergence in probability. So, I can say here that theta hat n is converging to theta in probability, and this type of consistency is called as weak consistency, right. Now, in case if you try to assume that this theta hat n is an unbiased estimator of theta, that is expected value of theta hat n is equal to theta, then it is sufficient to show that if the variance of theta hat n is tending to 0 as n goes to infinity, then the estimator is consistent. But remember one thing, this is only a sufficient condition, right. So, exactly on the same lines as we have defined the consistency condition in terms of variance of the estimator, similarly we can define the MSE consistency. That means an estimator is MSE consistent if MSE of theta hat n goes to 0 as n goes to infinity, and this is also a necessary condition for the consistency, right. So, in case if theta hat n is MSE consistent, then it is also weakly consistent. So, this implies that an unbiased estimator with its variance approaching 0 as the sample size approaches infinity is both MSE consistent and weakly consistent. That is what you have to just keep in mind. Now, let me try to take a very simple example to show you that how this sufficient condition helps us in finding or determining whether the estimator is consistent or not. So, suppose we have a sample x1, x2, xn of size small n from normal mu sigma square, then we know that the sample mean x bar n, which is like 1 upon n summation I goes from 1 to n xi. This follows a normal distribution with mean mu and variance sigma square upon n. So, if you try to see here that variance of x bar n is sigma square upon n, which goes to 0 as n goes to infinity, and therefore, this x bar n is both weakly consistent and MSE consistent. And similarly, you can now find the variance of any statistic and can check this condition and can find, right. But ideally, you must take the convergence in probability of that estimator. Now, let me try to take an example here to illustrate that how this consistency condition will appear when you try to look it from the data science point of view, and if you try to execute it on the R console, or if you want to determine whether a particular estimator is consistent or not, and suppose it is quite complicated to get it from the theory. So, one can also look into the simulated results and possibly can get an indication whether the estimator is consistent or not. So, let me try to take an example where we have observed a sample from a normal population with mean mu and variance 1, and here we try to see what happening to the consistency property. So, suppose we decide that we want to estimate mu, and we also know that expected value of x bar is equal to mu and its variance is sigma square divided by n. So, suppose we propose to estimate mu by two possible estimators, mu 1 hat which is equal to sample mean x bar, and mu 2 hat which is simply the summation of all the observations in the sample. Right. Now, in case if you try to find out variance of mu 1 hat, this is sigma square upon n, and the variance of mu 2 hat, that will be n times sigma square, because all the observations are IID, identically and independently distributed. Although we know from here that what is really going to happen, that as n goes to infinity, this value will go to 0 and this value will go to infinity as n goes to infinity, but we want to see how this behavior will look like when we are trying to execute it on the R console. So, now we have written here a program in which I am trying to generate the observation from the normal distribution, and then I am trying to compute the value of mu 1 hat and mu 2 hat, and then I am trying to find out the variance of mu 1 hat and mu 2 hat. Okay. So, if you try to see, this is the screenshot here, and now if you try to see, these are the values of the variances of mu 1 hat and mu 2 hat, and you can see here that as the values of n is increasing from 5, 10, 20 to 5000, the value of the variance is decreasing here. That starts from 1989 to, and it is decreasing to 2, but in the case of mu 2 hat, the variance starts from 49748 and it increases, and it is increasing to a very large value. So, this is actually not increasing, but this is decreasing. So, you can see here that from the simulation results, it is clear that the variance of mu 1 hat is decreasing as n is increasing, and the variance of mu 2 hat is increasing as n is increasing. So, I can be confident that at least this is not consistent. So, this is inconsistent. Right, and this is consistent. At least this is giving us a good confidence. Well, I will simply say that if you want to be 100% sure, you have to go through with the result from the theory. So, this is how you can look for the consistency property on the basis of simulated values in data science. Right. Okay, so now I come to another topic, which is about the sufficiency of the estimator. So, sufficiency is another criteria to judge the quality of an estimator. Now, in order to understand what is this sufficiency, let me try to take here a very simple example, and you please try to concentrate on the values which I am going to obtain. So, we consider here two independent random variables x and y, both are following the same distribution normal mu 1. Right. So, you can see here that the random variable x has information about mu, because mu is there, and y also has information about mu. Right. Both variances, they are actually known as 1 in x and y. Right. So, we can conclude by looking at the structure of x and y that both x and y contain information about mu. Now, we want to estimate mu. So, we try to consider here two possible estimators, right, and I try to compute say x plus y as one possible estimator indicated as mu 1 hat and x minus y as another estimator to estimate mu, and it is indicated by mu 2 hat. Now, if you try to see the expected value of mu 1 hat and mu 2 hat, it comes out to be here like this. For mu 1 hat, the expected value is twice of mu, and for the mu 2 hat, this is expected value of x minus expected value of y, which is mu minus mu is equal to 0. And if you try to find out their variances, so variances of mu 1 hat and mu 2 hat, they are the same, that will become variance of x plus variance of y in both the cases, and the covariance terms will become 0 because x and y are independent, and the variances of mu 1 hat and mu 2 hat comes out to be the same as 2. Now, you try to observe what is happening in these values, right. Here this mu 1 hat contains the value of mu, but now this mu 2 hat is not containing the value 0 when you are trying to take the expectation. So, now I can say here that mu 1 hat is following a normal distribution with the mean twice of mu and variance 2, whereas mu 2 hat is following a normal distribution with mean 0 and variance 2, right. So, now you can see here you want to estimate the value of mu, and this mu 1 hat contains the value of mu, but whereas there is no mu involved in normal 0 2. So, mu 1 hat contains information about mu, whereas mu 2 hat does not contain any information about mu. So, we can see here that mu 2 hat loses the information about mu, right, and we call this property as loss of information, right. So, you can see here that this x and y both had the information about mu, but with this mu 2 hat there is no information in the distribution which is related to mu. So, now what we need to do, in case if you try to look at this structure, we can conclude that if we want to make conclusion about mu using both x and y, we need to acknowledge that the dimension of them is 2, right, because there are two variables. On the other hand, in case if you try to use mu 1 hat, or say equivalently if you try to see mu 1 hat upon 2 will also have a normal distribution with mean mu and variance 1 by 2, right. In this case, we need to concentrate only on one variable, and we say that it has dimension 1. We are considering only on mu 1 hat upon 2. So, now looking at both the results, we can conclude that mu 1 hat and mu 1 hat divided by 2 provide the same information about mu as provided by the entire sample on both x and y, right. So, we can say that either mu 1 hat or mu 1 hat by 2 is sufficient to provide the same information about mu that can be obtained on the basis of entire sample. You do not need the entire sample, but you simply can use here these estimator, and they will give you the same information about mu that you can obtain if you try to use the entire sample. This is the idea behind the concept of sufficiency, and it helps us in reducing the dimensions, right. So, in general we can say that if all the information about mu contained in the sample of size n can be obtained directly by using this estimator, that means this estimator is sufficient, right. For example, if you try to take a sample say x1, x2, xn, and you try to compute the sample mean, then what will happen? The dimension of the sample is n, because there are n variables which have to be considered, and each of them is consisting or having the information about mu. But when you are trying to estimate the parameter mu by the sample mean, then also expected value of x bar is equal to mu, and through the sample mean it is sufficient to use only the one dimensional summary statistics to make inference about the mu, because sample mean is only unidimensional, x1, x2, xn, that will be n dimensional. So, you can see here you have reduced the dimension from n to 1 without losing any information, and that is why we call it that this is a statistics which is sufficient. Sufficient in the sense we do not have to look into the entire sample, but we have to look only into the value of this statistics. This is going to give us the same information which the complete sample can give us. Now, the question is how to find out such a statistics. So, first I will try to give you here the definition, the formal definition of a sufficient statistics, and then I will try to show you that how you can find it out. The finding of a sufficient statistics is not difficult at all. So, the formal definition is let x1, x2, xn be a random sample from a probability density function or a probability mass function which is given by like this f of x theta. Now, we try to define the sufficiency of the estimator. A statistics T is said to be sufficient for theta if the conditional distribution of x1, x2, xn given t is equal to small t is independent of the theta. Right. Now, you understand all the terminologies here. You know the statistics, you know the conditional distribution, you know the meaning of independent of theta. Right. So, this definition is extremely simple, but finding out the statistics is more simpler. Right, because this method, this definition does not give us a constructive way to find out a sufficient statistics. It can only verify that if a statistics is sufficient or not. That means, if you say that okay, x bar is a sufficient statistics for the mu or not, that can be verified using this definition. We have a theorem which is called as Neiman-Fischer factorization theorem. This helps us and this provides us a practical way to find the sufficient statistics. What is this? Let us try to understand the Neiman-Fischer factorization theorem. So, the same assumption that let x1, x2, xn be a random sample from a PDF or probability mass function f x theta. Now, a statistics t which is a function of x1, x2, xn is said to be sufficient for theta if and only if the joint density of x1, x2, xn can be factorized like this. This is here the joint density function of x1, x2, xn and theta. Now, this is being factorized into two parts, say gt theta and h of x1, x2, xn. So, you can see here that this h1, h2, xn, this is independent of theta, right. So, we say that where this h x1, x2, xn is a function which is non-negative and it does not involve the theta, right. And this quantity here gt theta, this is also a non-negative function of theta which depends on the x1, x2, xn, but that is depending through only t, and small t is a value of capital T, right. So, in a very simple language, you have to partition the joint density function into two parts such that one part is a function of only the observations and another part is a function of a statistics and the parameter, right. And this theorem holds for the discrete random variables also. And after this you have to just remember one result, that any one-to-one function of a sufficient statistic is also sufficient. So, if you can find a statistic which is sufficient and if you try to consider any other function which is a one-to-one function of this statistics, that will also be sufficient. And actually this definition can be extended to a case when my parameters are in the form of a vector. So, and then in that case we have a concept of jointly sufficient. So, for example, if I have the parameter theta 1, theta 2, theta q which are indicated by here underscore theta, then the statistics t which is a function of t1, t2, tk, well, k is not necessarily equal to q, then this t is jointly sufficient for this theta if the joint density function of x1, x2, xn and theta vector can be expressed into two parts where one function or one part is only a function of x1, x2, xn and it is independent of theta, whereas the second part is a function of t and vector theta, right. So, for the same definition extends over here also, that h x1, x2, xn is non-negative, it does not involve the parameter theta vector, and g t theta is also non-negative and it depends on x1, x2, xn only through t, and this is also a function of vector theta, right. So, the same definition continues here. So, and one thing, there is another concept of minimal sufficient. I am not going into detail, but let me just give you this idea that if suppose for a given parameter, if there are more than one statistics which are sufficient, then we try to see that which of the statistics is better. So, for that we try to employ here the concept of minimal sufficiency, and we try to see that which of the statistics is trying to reduce the dimension more, right. And that statistics which is trying to reduce the dimension to a minimum value, that is called as a minimal sufficient. Well, I am not going into the details. Those who are interested, they can look into the book, and this will try to give you an idea. But in general, when we ask for the sufficient statistics, then we are generally trying to find out the minimal sufficient statistics, because otherwise if you do not use it, then the whole sample itself will be sufficient, right. So, when you are trying to use the Neiman-Fischer factorization theorem, the statistic that you obtain is in general the minimal sufficient statistic. That is the advantage. So, you can see here, this is the advantage of using Neiman-Fischer factorization theorem for finding out a sufficient statistics. Now, let me try to take an example to show how you can employ this theorem to find out a sufficient statistics. So, let x1, x2, xn be a random sample from a normal population with mean mu and variance 1. Mu is unknown, and we need to find out a sufficient statistics for mu using the Neiman-Fischer factorization theorem. So, for that, first we need to understand that how we are going to find out the joint distribution function of x1, x2, xn, which has to be partitioned into two parts. So, you can see here in this case, if you try to find out here x1, x2, xn. So, since you are assuming that the sample is random, so all x1, x2, xn are independent. So, they can be written as the product of f of x1, f of x2 up to here f of xn, right. So, if you try to write down here the PDF of normal distribution, then their product can be written here like this: 1 upon square root of 2 pi raised to the power of here n exponential of minus 1 upon 2 summation I goes from 1 to n x I minus mu whole square. Now after this, if you try to partition it into two parts, we can obtain here the following two partitions. You can see here, first try to look here, that you can see here this is a part which is depending only on x1, x2, xn, right, and this is independent of any parameter, say here mu. And similarly, if you try to look here in the second part, which is here like this one, this is actually here trying to indicate the gt theta of the Neiman-Fischer factorization theorem. So, in this case your theta is mu. So, this is actually a function which is gt mu, and you can see here this is depending only on the value of x1, x2, xn and mu, and you can see here the value of t is I goes from 1 to n summation xi, that is the sum of all the sample values, right. So, here now I can say that in this case we have found that t is equal to summation xi, and summation is going from I goes from 1 to small n. So, this is only the sum of sample observation, and based on this, now using the Neiman-Fischer factorization theorem, we can conclude that t is equal to t x1, x2, xn is I goes from 1 to n capital xi. This is a sufficient statistics for mu, and you see since you have understood that any one-to-one function of a sufficient statistics is also sufficient. So, we can also consider the function summation xi upon n, which is simply your sample mean. So, instead of writing the sample the sum of the sample observation, we can also say that sample mean is sufficient statistics for mu, because this is a one-to-one function of summation xi. Right. On the other hand, if you try to see means another statistics t equal to square of the sample mean x bar square is not sufficient for mu, because it is not a one-to-one function of summation xi, right. Hence, now we can conclude that x bar is a function of the sufficient statistics, and hence a good estimator for mu, and it is summarizing the sample information about the parameter of interest, which is here mu. And now we consider one more example where we try to get a sample from a normal population with mean mu and variance sigma square, and both mu and sigma square are unknown to us, and we try to find out their sufficient statistics using the Neiman-Fischer factorization theorem. So, we consider here the joint distribution of x1, x2, xn, which can once again be obtained as a product of f of x1 into f of x2 into f of xn, because the observations are independent, and that we can obtain exactly in the same way as we have done in the earlier example. So, if you try to write down the joint PDF of f of x1, x2, xn, this can be written here like this one. Simply multiply all f(x) i's from the normal mu sigma square, and now this part can be partitioned into two parts. You can see here this part, this is the part number 1, where you can see here this part is independent of mu and sigma square, and this is only here a function of here h of x1, x2, xn, where h of x1, x2, xn is equal to here 1. Now, the second part here, you can see here this is here like this. So, you can see here now this is a function g t mu sigma square, and where this t is a function of x1, x2, xn, which is here like this summation xi and summation xi square, and summation is over the sample values. So, now you can see here that here this t is equal to function of x1, x2, xn, which is summation xi and summation xi square, and here the parameter here is theta vector, which is mu and sigma square. So, I can say here that the summation xi and summation xi square, this statistics is jointly sufficient for mu and sigma square, right. Okay, so now we come to an end to this lecture, and now you can see here that I have given you a fair idea about the statistical properties of this estimator. Now, I think the time has come where you have to just practice these things in a separate way. For example, how to show unbiasedness, how to show consistency, how to find a sufficient estimator, etc. You have to take one example, and then you have to look for these properties, that how you can verify them in a theoretical way as well as in a numerical way. Once you can do this thing, then all that these properties will get settled down in your mind, and obviously when we are looking for a good estimator, we would always like to have all the properties in that estimator, but these are the different properties that we expect to be in a good estimator. Now, the next question is this: many times we are continuously we have talked that this estimator, how to get this estimator. So, in the next lecture I will try to give you two methods, method of movements and maximum likelihood method, which helps us in finding out a good value of the parameter as a function of sample values, that is the statistics. So, but before that, it is very important that all these properties should be very clear in your mind. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.